Okay. Yay. Where we at? Tuesday, so Friday. Mean, median, measures of center, range, standard deviation, IQR, spread. Which one's appropriate? Anything that y'all need, I need cleared up about that stuff y'all got confused about? Everybody okay with all that? Homework, again, I looked at, ironically, the ones that are most missed are the ones that required as many blanks. The more blanks, the more chances of missing it. I don't think it's that difficult. I did learn this. If you have data in the question, rather than typing all that in, you can hit hint and it will give you the data that you can copy and paste into Desmos. So I don't think the question lets you copy and paste, but if you hit hint, it will. So any question that has data, rather than you typing it all into your calculator and or Desmos, you can hit hint and it will bring up that data. You can copy it from there and paste it into Desmos. I don't mind you guys doing that. All you're doing is, you're just saving yourselves keystrokes. And I don't mind you guys doing it. That is not what I would consider cheating by any stretch. Okay? Copying the actual question and throwing it in AI is. But copying the data and putting it into a calculator is not. Okay, everybody okay with all that? Good? Nothing else? Y'all good then? Mean, median, measures of center, IQR, standard deviation, and range, measures of spread. We talked about shape on Thursday. So we know shape, we know the center and the spread, and now we're going to talk a couple of other things about it to finish up lesson D. So here we go. Start us up. That's what Mick Jagger would say. Anybody? This would start me up. All right, here is our learning targets for today. As we're getting going, guys, let's close our computers, please. Let's focus in. We got big, I don't want to say long topic today, but again, this is starting to get a lot of stuff combined into for this one exam, okay? So today, what our plan is, identify outliers. We're not going to identify outliers. We're going to find them mathematically. Make and interpret box plots. You guys have probably seen a box plot before. A box and whisker plot is what they were called. We're going to calculate and interpret percentiles. So we're going to find and calculate and interpret percentiles. Then we're going to calculate and interpret a standardized score. You may or may not have seen a z-score before. And then we're going to analyze the effect of transforming data. So 1, 2, 3, 4, 5 big bullets today. Okay, here we go. Uh-oh. Well, you don't want that. Exit. Let's go here. Load it. Turn that on. Let me hit refresh. And that should remove all this stuff. It did. Now we'll go back to hit play. Sorry. Okay, outlier. Outliers. Come on. Good gracious. How to identify outliers. It's called the 1.5 rule. It's called the 1.5 rule. And what you are going to do, you guys already did from Friday, is first thing you're going to do is find the IQR. Okay, find the IQR. So we're going to do Q3 minus Q1, right? Q3 minus Q1. So find the IQR. There you are. Find that IQR. This is a multiplication sign. So multiply the IQR times 1.5. Multiply the IQR times 1.5. Okay? Once you do that, that number is going to get Q1 minus that number, 1.5 IQR. Anything smaller than that, anything smaller than that is an outlier. 1.5 times the IQR, take Q1 and subtract it. Don't flip-flop that. Okay, this matters. This order matters. So it's Q1 minus that number. It's possible that's a negative number. It's possible that's a negative number. If that's negative, there's not going to be outliers on that side. And then you're going to take Q3 and add that to it. Okay, so Q1 minus 1.5 IQR, Q3 plus 1.5 IQR. So take the third quartile and add it. Take the first quartile and subtract it. Anything smaller than this number or anything larger than this number, those are outliers. Okay, and it's just called the 1.5 rule. It's a 1.5 rule, and it will say use the 1.5 rule, or are there any outliers according to the 1.5 rule? Pencils, y'all are still going. Questions, questions, questions. IQR, Q3 minus Q1, times 1.5. Subtract it from Q1 and add it to Q3. Subtract it from Q1, add it to Q3. Anything larger than that, anything smaller than that. Here we go. Catamarans, going back to that same catamaran problem, right? They're built with the two hulls. They have water, fresh water on there. We don't want them to run out of fresh water. Certain catamarans are built to withstand passage. Here are the freshwater capacities of these 19 ocean-going catamarans. So there's the fresh water in them, right? And what they're going to ask us to do is say, use the 1.5 rule to identify the outliers. Well, we've already learned we got to put this in order. So put it in order. We did that. Once we put it in order, we got to find the median. Once we found the median, we find the first half of the median and the second half of the median. And there we go throughout this great mathematics we have. We have 206 subtracted 145, and we're going to get 61. So slowly catch up. TJ, you don't close those computers. I'll get in trouble. If admin comes in, you don't see computers or get mad at me. Won't get fired yet. I'm one will you away from it, but okay, everybody okay with that number, right? The IQR. We found that, and your calculator's going to find that. Most times they're going to give us that. We're going to take that IQR and multiply it by 1.5. So 1.5 times 61 is 91.5. Okay, so there's my number right there, that 91.5. I'm going to subtract that from Q1. So Q1, 145 minus 91.5 puts me at 53.5. 53.5 is down here. So there are no low outliers. 79 is bigger than 53.5, so there are no low outliers. And then I'm going to take Q3, the 206, add that same 91.5, and I'm going to get 297.5. Outlier at 360. 360 is an outlier. So we will simply say there are no low outliers, and there is one high outlier at 360. There are no outliers because none of the catamarans are below 53.5, and there is one outlier at 360 because it is higher than 297.5. Yeah. No. Yeah. So if you got all this stuff right here, then you wouldn't have to say. I mean, you would just say there's one at the high end, and because it's greater than that, 360 is greater than 297.5. There's one higher, and there are none lower than 53.5. That's perfect. That's good. Yeah, they don't. Everybody else okay with that? Good question. I don't know how much work they're going to require for this kind of stuff. Again, picture yourself on the AP exam. You got a computer. You're trying to type all this stuff. So I don't know exactly what you're going to end up doing. For me, it's paper and pencil. So I think it's a little bit easier. Okay, so Q3 times 1.5. Subtract it from Q1, add it to Q3. Smaller than that, larger than that. Those are outliers. Questions? Y'all okay? Good, 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 good. Clicky, click, click. There is another way that somewhat we don't use it. Don't use it. They're going to call it, you're going to take the mean, the average, multiply that by 2 standard deviations. I think you're going to add that. More than 2 standard deviations from the mean. Yeah, that's plus. It doesn't matter. You're not going to use it. Don't use it. There are some that will. But here's the issue with using this. Think about this, guys. If you have an outlier, it's affecting this and affecting this. You're using the outlier to decide on if it's an outlier. It's not a good way to do it. Remember about the resistant, right? The IQR and the median are resistant. They're not affected by those outliers. So you're using stuff that's not affected by it to see if it is an outlier. Whereas if you're using this, you're using that outlier to decide if it's an outlier, and that just almost doesn't make sense. So there are people that talk about using the 2 standard deviation rule. I don't think it's a good one. And what they're going to say is, unless otherwise indicated, we always use the 1.5 rule in AP Stats. And most everybody does. Okay? It's important to identify outliers for several reasons. Okay? They might be an inaccurate data. It's possible you flipped. It was supposed to be 35 and you put 53, right? That's possible. Bless you. They can indicate a remarkable occurrence. I don't think that 160 was inaccurate data. Not, is it 360? Sorry, 360. I don't think it's inaccurate. I think that's just either a really big catamaran or one that was really concerned about water. I mean, that's a remarkable occurrence. Y'all okay with that? 2 things. And then the other one is, of course, they can heavily influence the values in the summary statistics, such as the mean and the range and the standard deviation. That's why if there's possible outliers, you don't use the mean and don't use the range and don't use the standard deviation, because those outliers affect those 3 numbers quite a bit. It's just things that, like, again, you know this, it makes sense to you, but it's just the aha moments, right? We want to make sure that you realize, hey, why is that what happened to that number way out there? Is it just wrong data? Is it remarkable, or is it amazing that that number's out there? And I don't really want to use it to calculate these 3 things because that number is so far out there. Beautiful. Boom, 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 boom. Everybody good? 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 Clicky, click, click. Box plots. Box plots. Bullet number 2 today. Box plots. Click. Another graphical option for quantitative data is a box plot, sometimes called a box and whisker plot. A box plot summarizes distribution by displaying 5 important values within the distribution, and it's known as the 5-number summary. 5-number summary. Here are those 5 numbers. One of them is called the minimum. You might guess what another one might be if it's the minimum's one. You okay? So maximum's one of them. And guess what? This one's Q1. Got a wild guess what the other one might be? Q3. And then the fifth one would be the median, Q2. Okay, whoop, too fast, sorry. So that's the 5-number summary. It's very, very possible that they ask you, what is a 5-number summary? Okay? Given the 5-number summary. It's just, these 5 numbers tell me a lot about the data. They tell me a lot about the data. So the minimum and the maximum, Q1, Q3, and the median. And I can find outliers pretty quickly because I can find the IQR, multiply it by 1.5, add it to this. If this is bigger, you know there's an outlier. If this is smaller, you know there's an outlier. I want y'all to listen to what I'm going to say in just a second because it was highly, highly missed for the past 19 years. So I give you the 5-number summary and I'll say, are there outliers? And so students do this. They subtract that and they do the 1.5 and they add it to this and this number was bigger. And a lot of students says there is an outlier. And that's wrong. No, there is this one's outlier. There is an outlier. The maximum is an outlier. What's wrong with it? It's a little trick. This one's an outlier. Is there a outlier, or is there at least one outlier, or are there outliers? You'll kind of see what I'm saying? You don't know how many there are, but you know there's at least one. There has to be at least one because this one's one, but you don't know if there's another one or not. That's a bad thing about the 5-number summary is it does not retain the original set of data. You don't know how many outliers there are. There could be 5 or 6 outliers. There might be, there can't be 0 because there is one. There is an outlier that was dinged on the AP exam because there is a, but there also could be more. So there is at least one upper outlier is what students had to say. That question is no longer valid because we're not going to do that, I don't think. I might be able to, I don't know. I didn't like my test, so I'm going to redo it after I'm going through the lessons. Yay, question, good? Clicky, click, click. Okay, we hear that the typical depth of the ocean is greater than 2 miles. The depth of the ocean is 2 miles. Think about it. That's deep. That's crazy. Like you're not swimming down there. You're not even putting a boat down there. Anyway, to investigate this claim, we take 14 randomly chosen locations, and here are those depths. Yay with all that? Beautiful. Make a box plot. So if I'm going to make a box plot, the first thing I got to do is find the 5-number summary. And we'll speed up this process a little bit because I really believe that every one of you guys can find the 5-number summary. The first thing we got to do is put the data in order. So I'm going to put it in order, and I'll tell you that between here and here is the median, and I'll just go ahead and tell you that's 4030.5. And then we're going to find the lower median, which is 34.99, and we're going to find the middle median, or the upper median, I'm sorry, which is 51.61. And of course, you can see the minimum and you can see the maximum. Soak that up. I really believe that you guys can find that by now, as you guys already did that for homework. Now, the next thing we need to do is figure out if there are outliers. So here we go again. We're going to figure out if there's outliers. So we're going to do this number minus this number to find the IQR. And I'll go ahead and tell you that that number is 1662. The IQR, 1662. And then what am I going to do with the 1662? Multiply that by 1.5. And so 1662 times 1.5 is 2439. 2439. I'm going to subtract that from Q1. So 3499 minus 2439, you guys would punch all that up and I would get 1006. Oh, 1006. Two outliers. Two outliers because I do have the data. Then I'm going to take the upper quartile, which is 5161, and add that 2493, and I'm going to get 7654, and I don't have any on the upper end. Soak all that up. A lot of you guys are writing. I'm throwing out a whole bunch of numbers. I don't want to do it too fast, but I don't want to spend a whole lot of time doing simple math. So minimum Q1, median Q3, maximum. Bigger or smaller than that, bigger than that. There are none bigger than that. There are two smaller than that. Hadn't made the box plot yet. That's what we're getting ready to do. Click. To make a box plot, we're going to make a number line. Anybody can make a number line. You can start with anything you want. And you can go by anything you want. I would not start at 2,000 because the smallest number is 205. The biggest number is 6,000. So they started at 0 and went up to 6,000. But you can go by whatever you want, do whatever you want. There is no reason. You do not have to start at 0. It's just a number line. It can start wherever you want to. And then I'm going to draw a box around Q1 and Q3. A box around those. So here is Q1, here is Q3. Get close. You don't need a ruler. You don't have to get precision. Just get close. Get close. I will say that some students, I have seen them do this on a bar chart many times. They will put 205, then they'll put 3499, and then they'll put 4030, and then they'll put 50. They're not actually using a number line. They're just putting the numbers down. And every box plot looks beautiful. It looks just like that. Well, that's not what it looks like. You shouldn't do that. Okay? Make sure it's on a number line and make sure it looks good. Okay? Whoops. All right? After you draw a box around Q1 and Q3, draw a line where Q2 is, or draw a line where the median is. Draw you a line where the median is. Maybe you've made box plots before, I don't know. If you have, you probably have not done this, what I'm getting ready to do. Normally, we put a point at the minimum and we put a point at the maximum, and that gives me my whiskers. So the whiskers for the box. Normally, AP Stats does not do that. So we're going to put 2 points at 205 and 749. You can put them as stars, you can put them whatever you want, but put those 2 points as points by themselves. Those are outliers. We want you to be able to graph outliers all by itself. Okay? And then what we're going to do is do my whiskers part. So my whiskers is going to go out to the max, which is right at 6,000, just a little bit less. And so that comes out here, and you can put a dot, or you can just put a dot, whatever. It doesn't have to be anything pretty. And then the bottom is going to go to this number here, the 1372. That's the smallest non-outlier. Here's a couple mistakes. One mistake is I already showed you, right? They don't go by common intervals. They don't make a number line. That's one mistake. The second mistake is they put this right here down to, what's that number? What was that number? 1006. They put it down to 1006. They don't put it here. Here, I'm sorry. 1006 is not even a point. So don't put it down to 1006 where the outliers start. Don't start it there. Put it to the last point that's not an outlier. The last non-outlier value. Don't put it all the way down to the 1006 where outliers start. 1006 is not a point. Okay, here we go. You got the minimum, you got Q1, you got the median, you got Q3, and you got the maximum. Wowzers. Hurt. If they're outliers, put them by themselves. Then go to the smallest number that's not an outlier, box around Q1, Q3, median, go to the maximum that's not an outlier. The maximum's not an outlier, so I can just go to the maximum. Easy peasy making it. How many of these you're going to have to make? Probably none. It's hard to do that with a computer, with a keyboard. Yay? Good? No pencils. Does the graph in part A support the claim that the typical depth is greater than 2 miles? Thank goodness they turned that to meters for me, which is 3219. That's, what was that number? 34 something? 34, that's 35. So this is 35. Here's 3219. Does this graph support that the typical depth is more than 3219? 25%, 25%, 25%. 75% of my samples are greater than 3219. Yeah, most definitely. In fact, 50% are greater than whatever that was, 41 something. 50% are a whole lot taller than 3219. Y'all okay with all that stuff? So I don't think you need to validate it with both those things. I think just saying that 3499 is Q1, which means that 75% are greater than 3500, which tells me that the typical depth of the ocean is greater than 2 miles. That definitely tells me that the depth or the average depth or the typical depth is greater than 2 miles. May have I got bad samples, I don't know, but any question about that statement? Boom. Box plots provide a quick summary of the center and spread. Box plots show the quickest, right? If I put a dot plot up there, it's not as quick as this. If I put a stem and leaf plot up there, it's not as quick as this. And the reason why, it tells me immediately what the center is. I can easily see without a whole lot of work at all, the center appears to be right at 4,000. It tells me the median really quickly. It also tells me the spread. It tells me 2 spreads or 2 variabilities. I can use the IQR or I can use the range. I typically don't like the range, especially if there are outliers. Yes, you include the outliers with the range, but it tells me the spread really, really quickly. And then it also tells me that there are outliers really, really, really quickly. The thing that box plots don't tell us is the shape. It kind of tells me it doesn't show peaks, it doesn't show gaps, it doesn't show clusters. It I could show clusters, but if there's a really, really small space between two of them, that would probably be a cluster because it's 25% of the data. Yeah. This data is probably skewed left. There's more data here than here. I mean, this is 25% of it. That 25% is a lot longer than these 25%. So I'm thinking it's probably skewed that way. We'll go with that, but we aren't for sure. This is kind of like a histogram. It does not retain the original set of data. I can't tell you if that was actually a point. It's the median. Yeah, but it could have been the average of two. In fact, it was the average of two. So it may or may not be a point. So I don't know. Now, this, I know that there are 2 points here. Give me a split second. Boom. Calculators, yeah. So we've done stat edit. We've done all that stuff, right? If you hit y equals, that's all your functions. That's every other class but this class. Typically, we don't put functions in here. If you're in any other math class, then you got functions. Probably get them out of there. Okay? I tend to, every once in a while, look to make sure there's not one down there in zero. Sometimes they hide one down there. Okay? I also make sure if I'm in another class that these are not highlighted, because if they're highlighted, they're going to mess up your functions. That's bonus points. But if you're in this class, you don't have to worry about it. I don't worry about these things, and those plots are what can graph things. And to get the plots, you hit second y equals. Second y equals turns on your plots. Here's plot 1, here's plot 2, plot 3, and I typically only plot one thing at a time. And I'm going to plot number 1. So when I hit number 1, I'm going to look at it. This will turn it on and off. So it just toggles back and forth. Right now it's on. If I go over here, now it's off. This goes to on. Is that your little numworks? What? Is that yours? No. Oh. I was just borrowing it. Oh. Oh, you do have one like that? No. Oh. I just found it. Oh, it's mine. Oh, it's yours? Yeah. It's okay. You can use it. I was just on a table. Yeah. Azure use. What my little other kid used. That's. Oh, it's awesome. Oh yeah. I don't know how to use that. It's awesome. Yeah, it's so much easier to use in this thing. Okay. So you have your data in there, L1, right? That's a scatter plot. You need L1 and L2 to do a scatter plot. That's a time series plot. You don't use those. There's a histogram. So your calculator will graph histograms. Be careful about letting it choose widths, but it will do it. And then notice this one here looks like a box and whisker, and it has 2 dots on it. And this one is just a plain old box and whisker. This is the one you're used to seeing. This is the one we use in AP Stats because it shows the outliers. A lot of times, this one and this one will look the same. And then this one's a normal probability plot, and I don't think we'll use that anymore. So when I turn this on, of course, you ask you where your list is coming from. So your data should be in L1. And if you go down to frequency and whatever else, and when I hit graph, you probably won't see it. I do see part of it. I see part of mine. Okay? So anytime you graph something in this class, always zoom 9 stat. Zoom 9, and it's going to drop. Oops, sorry. I put an outlier out there so you can see it. It was too big. Let me get rid of that 200. Actually, there. Zoom 9. Whoops, 30 wasn't an outlier. It's all right. Graphs it. Good enough? So you can see all the data points you want to. If you have to, you can actually hit trace, and it will tell you that the median is 5.5. And if you go to the right, it'll tell you what Q3 is. And if you go to the right, it'll tell you what the max is. And if you go to the left, it'll tell you what Q1 is. And if they had outliers, you would find the outliers also. Just to show you your calculator can do it if you need it to. Desmos will graph them also. I don't care what you use, and we'll never tell you not to use it. Y'all okay? Good? I want you to use your calculators. All right. Boom. 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 Apply. Keep. Slideshow. Any questions about box plots? Median, interquartile shows outliers. Box plots don't give a complete picture because they do not retain the original data, the individual data sets. Just make sure you remember that. I said dot plots. I think box plots and histograms. Box plots and histograms don't retain it. Dot plots and stem and leaves do. Dot plots and stem and leaves do. The other two do not. Click. It can't show us peaks. It can't show us gaps. It can't show us clusters. Although I still think clusters could be debatable. I have no idea from this. I really think it is skewed to the left. I think it's skewed to the left. All right. Third thing today. Third bullet, percentiles. Percentiles. One way to describe an individual's position is the percentile. The distribution of quantitative is to calculate that individual. Remember, individual doesn't have to be a person. Is their percentile, okay? So let me tell you what a percentile is, all right? A percentile of a distribution, quantitative, is a value with P%. Oops, forgot to turn that on back onto a marker. P% less than or equal to it. P%. You are in the so-and-so percentile, right? Me and my bride had our kids. We took them to the doctor and they told us that they were in a so much percentile of height. They're in so much percentile, that was it, height and weight, right? That meant that, that there were that many percent lower than them. So the percentile, P% less than or equal to that number. Less than or equal to that number. It can't be 100% because that number is part of it. Can't ever be 100% because that number is part of it. Can't be 100% below that number because that number is part of it. Because it's equal to or less. So because that number is part of it, it can only be in the 99th percentile. Percentile. Click, click. Percentiles are specific locations in a distribution. So an observation isn't in that percentile. Please be careful about that language. There's a reason why we put that. Okay? It's not in the 84th percentile. There's a bunch of numbers in the 84th percentile. It's at the 84th percentile. Or it is the 84th percentile. Is or at, but don't say in. There's a bunch of them in it. There's a bunch of them in it. Every one of those numbers is in the 84th percentile. That number is at the 84th percentile. Or it is the 84th percentile. So be careful about your language on that. Okay? Click, click, click. Oh, the median is the 50th percentile or right at it. The median, the first quartile is the 25th percentile. The third quartile is the 75th percentile. That means there's 25% above it, 75% below it. Again, things that I think are easily understood and should already be known. I want to make sure. No pencils. Good. Clicky, click, 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 click. Most people always think we want a high percentile. We don't always want a high percentile. If we're talking about weight, I don't want to be in the 98th percentile of weight. Yes? I don't want to be in the 98th percentile of cholesterol level. So just understand it doesn't always mean a good thing to be in the high percentile. People are living longer now than any other time recorded in history. This is a blessing, but also a challenge for many countries because they have to adjust to the needs of aging populations. One statistic, remember what statistic is, right? That's a number that measures a sample. Important to the social scientists who study this phenomenon is life expectancy at birth. The stem and leaf plot shows the life expectancy at birth of a recent year for 41 countries in Central America. There's that stem and leaf plot. What's the shape of that stem and leaf plot? What do you want to call it? Remember, there are wrong answers, but there are right answers. Skewed? Symmetric? If you want to say skewed left, I would better put the word slightly in front of it for sure. I think if you want to put symmetric, I think you're okay still too. Picture this, right? These are sixes, these are sevens, and these are eights. So a 6, 7, and 8's pretty darn close together anyway. Fair enough. I don't know how much more the tail has. So, but I think you're okay with skewed to the left. It just better be slightly skewed to the left, very slightly. But I think you're okay with symmetric. I don't think you're okay with skewed to the right. And I don't think you're okay with uniform. Okay. Click, click, click. Calculate the percentile for a country with life expectancy of 78 years. How many countries are up here? 41? 41. If I want the 78 years, 78's right here. I can count all those numbers, or 1, 2, 3, 4, 5 above 78. So if there's 5 above 78, that must mean that there are 5, 41, 36 below. So that percentile is 36 out of 41. There are 36 numbers 78 or less, which puts it at 0.878. 0.878. So this country is at the 87th, actually 88th percentile. It's at the 88th percentile, and that means 88% of the countries have life expectancy of 78 years. Of the countries? Yeah, 87% of the countries have a life expectancy of 78 years or less. 87%. That's a pretty high number. Like 9 out of every 10 is expected to live 78 years or less. Kind of seems reasonable. Everybody okay with that number? It's a big thing. Less. Make sure you mention less. Okay? The life expectancy at birth for Peru is the 39th percentile. How many years is that? 39th percentile out of those 41 cats. 15.99, 16. Now, that's not 16 years because that's not even a choice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 72 years. "72 years old" is at the 39th percentile. 39% of the countries you're expected to live 72 or less. Peru is at that 72nd percentile. I'm sorry, 72nd years. Because 16, 72, what? Peruvian? A Peruvian newborn is expected to live 72 years. I didn't know that's what you called up somebody that lived in Peru, a Peruvian. Pencils, none. Boom, boom. Okay, we're good? Now z-scores. Z-scores or standardized. Standardized. Mathematicians are lazy. We try to abbreviate everything we can. Everything we can, we try to abbreviate. Standardized, we got tired of writing, so we just called it Z. Another way to describe an individual value's position is to give the standardized z-score. So let me tell you what a z-score is or does. Okay? The z-score will tell you how many standard deviations. How many standard deviations a value is from the mean. Not only does it tell you how many standard deviations it falls, it also tells you which direction. Which direction. You're either above the mean or below the mean. If you're one standard deviation, you could be one standard deviation above or one standard deviation below. Okay, we talked about standard deviation. Remember, standard deviation is the average distance from the mean. And so you're either that one standard deviation away, you could be two standard deviations away, you could be 0.5 standard deviations away. You could be 0 standard deviations. If you're 0 standard deviations, then you must be equal to the mean because you're not far away at all. You are the same. Z-score. Yay? Good? Click, click, click. Here is the formula for that. Okay? I'll give you a blank. Z equals value minus mean. Value minus mean over the standard deviation. Some people like to put variables. Z equals x minus x bar. X bar is the mean. S is the standard deviation. I do not think that formula is on your formula sheet. I don't think it is. Yay, quick, go back. Let me go here and delete this again. Boom, go back. Z, value, mean standard deviation. Click. Values larger have positive z-scores. If you're larger than the mean, you have positive z-scores. If you are lower than the mean, then you have negative z-scores. Go back to your formula really quickly. I'll go back, right? It's the value minus the mean. So if you are lower than that, then you're subtracting a bigger number, which would make it negative. Negative divided by its standard deviation is always positive. So if it's a negative, you are below the mean. If it is positive, you are above the mean. If you are 0, you are at the mean. Standardized z-scores have no unit of measurement. The unit of measurement is standard deviation. You're not 1 unit. You're not 1 mile. You're not 1 inch. No, you're 1 standard deviation. So it has no unit of measurement other than the standard deviation. Okay, everybody good? Previous alternate example reported that data on life expectancy of 41 different countries. Same question, same data. This is again very common. There's the 41 countries. There is the mean. There is the standard deviation. There is the minimum. I'm guessing that is Q1. I'm guessing it didn't get copied for some reason. There is the median. I'm guessing there's Q3, and then I'm guessing there's the max, and that's really, really common for them to give you all that values. They're going to tell you that Peru have a life expectancy of 72 years, and it wants to know the z-score for that Peru. So the z-score for Peru is equal to that score minus the mean, which is 73.415, and we're going to divide that by the 4.159. Get your little fingers working, boom, 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 hit enter, and you're going to get something like negative 0.34. You knew it was going to be negative because it was smaller. Peru is below the mean. The life expectancy for Peru is 0.34 standard deviations below the mean, less than the mean. Guys, they're going to want that word. They're going to want less than. They're going to want the standard deviations. And then, of course, the context. They really don't care about the 0.34, truthfully. I've seen students miss that part and still get full points. We don't grade the actual math. We grade your understanding if you know what that number's telling me. It is 0.34 standard deviations below the average, below the mean. It's below because it's a negative number. It's below because 72 is smaller than 73. 73 on the number line is here. 72 is here. We're below the average. Not by much. 0.34 standard deviations. Easy, okay with the standardized score? Click, click. The life expectancy for Panama has a z-score of 0.62. Has the z-score of 0.62. What is the expected length of time a Panamanian can live? Well, I don't know, that's X, but I know the mean is 73 point, is it 415. And the standard deviation was 4159. Point, was it? Point? No, 4 point. Dadgummit. Holy cow, looky here, guys. You got to solve for a variable. Almost a one-step equation. Maybe it's two-step equation. Multiply both sides by 4.159. Move that 73.415 to the other side. And when you do all that stuff, you're going to get 75.99 or 76. A Panamanian newborn is expected to live about 76 years or just under 76 years. Don't say 76 years or more because that's wrong. If you say 76, you're okay because it's 75.99. However, I would like just under 76 years. Everybody good? You get the z-score, you have a value, you have to do a little bit of algebra. I know, I'm going to make you do some math. Most of you are happy, some of you are not. Click. Last thing, last bullet. A lot of this should make sense to you, I hope. Sometimes useful to transform data when analyzing a distribution of quantitative variables. We may want to change the units of measurement for a data set, or perhaps a measuring device is calibrated incorrectly. We're measuring something and it's just a wrong unit of measurement, or it's really loose at this end, it's just calibrated wrong, so we have to adjust for that. Click. Students' test scores. Person did really well. Person did not do well. These all did this. We have no idea what any of this says because we have no numbers. Click. There's 25 students. The mean is 35. Yuck. Standard deviation is 8. The minimum is 12. Ugh. Maybe this wasn't a 100-point test. The maximum was a 48. Boy, that kind of changes this whole data up, doesn't it? You'll kind of see the importance of what I'm talking about. Of you just looking at this, it tells me a good story, but then it told me a really bad story. Everybody okay with all that stuff? So 5 points are added to students' test scores. Ooh, thanks. That's really nice. 5 points. Didn't have to get any. So what's it going to do to all that data? Just move it, right? Is it going to make it wider? Going to make it narrower? Just going to move it, yes? So the minimum is no longer at 12, it's now at 17. And the max is no longer at 48, it's now at 50, whatever. The median is no longer at 38, it's now moved. Okay with all that stuff? So it shifted everything down those 5 units. And it changed, it doesn't change n, that's still the sample size. It changed the mean. It did not change the standard deviation, but it changed the minimum, it changed Q1, it changed the median, it changed Q3, and it changed the max. Careful. Did it change the IQR? No. It was these numbers. Now it's these numbers. The IQR is still the same. So when you add or subtract a number to a set of data, it changes the center. It changed the mean and it changed the median, but it did not change the spread. It didn't change the IQR. It didn't change the standard deviation. It won't change the range. Did it change the shape? Didn't change the shape. So here we go. Boom, boom. Adding the same positive number adds that number to the center, or subtracts. So if I add a number to every single data value, it's going to add it to the mean, okay? And the median. It's going to add it to the center. However, the variability does not change. The range, the IQR, and the standard deviation does not change, and the shape does not change. You don't have to have this memorized, guys. You guys can think about it. Okay, if I add something, all it does is shift it down. If I subtract something, all it does is shift it down. That's it. It's not going to change the shape. It's not going to change the spread. It's going to change the middle. Okay, it's going to change the middle. We need to understand that. Please remember, right? I can't tell you how many test scores I've seen when I add or subtract a constant and students change that spread. They change the variability. It doesn't change. All it does is move. It doesn't change. Okay? You guys can get in such a habit of y equals mx plus b. We're going to use y is equal to ax plus b. This b will not affect the standard deviation. It will not affect the IQR. It will not affect the range. It does affect the center. Click. Multiplying. multiplying. So here's that test score. I'm going to multiply everything. Now, if I multiply it, well, that's going to double this, and it's going to double that, but it's also going to double the spread. There's that new mean. Boom, boom, boom. Let's go to it. I'm sorry. Here we go. Here it is, right? So the new mean, or the mean was 40. Now the mean is now 80. The median was 43. Now it's 86. This distance was 10. Now it's 20. So multiplying will affect the center. Dividing will affect the center. Multiplying will measure or change the variability. Dividing will change the variability. So it changes those two things. Let me go back real quick. Did it change the shape? It just made it out bigger and shifted it, but it didn't change the overall shape. Y'all okay? So the shape does not change. Oh, okay. Does not change the shape. Okay. Question about that. Let's do an example. Putting it all together, adding, subtracting, and multiplying. Here we go. What happens if we transfer quantitative data to adding and subtracting, multiplying to constant? We just learned fact about transforming. We already know all this stuff, order of operation. So here we go. We got Salvati Pasta Emporium. Whoever. Pasta Emporium is an authentic Italian restaurant. I just ate. That sounds pretty good, though. Makes its own pasta. The rigatoni pasta is very popular, and customers buy a 32-ounce boxes of rigatoni to cook at home. The employees who fill the boxes aren't perfect. However, the actual amount in the box varies. Oh, so the actual. To check their work, Miss Salvati owns it, selected 50 boxes at random and weighed them. There they are. They're supposed to weigh what? 32? Uh-oh. Got a lot of unhappy customers. A lot of customers not getting 32. There's some getting a little bit better. There's not very many getting 32. Here's the summary statistics. The mean is 31.7. It's not too far off. They're making a little bit of extra money. There's the median, 31.7. I don't know if that's an outlier or not. They must have fell asleep that day and really shortchanged them. Soaking all that in, just remember the story that it's telling me good stuff, information, okay? Worried the boxes were being underfilled. Sounds like a good worry. Miss Salvati added an extra 0.5 to all the boxes. Were you locked out? Oh. That was so nice of you. Oh. Told you we're a team in here. So her customers wouldn't feel cheated. Calculate the mean of the rigatoni after I get the 0.5 with it. Well, I'm going to get over here and I'm going to say, and then it's going to say, will they be satisfied? X bar equals mean 31.7. I'm adding to that the 0.5. And if I add 0.5 to that, 31, 7, 8, 9, 10, 11, 12, I'm going to get 32.2. That's what the average is. Now are the customers happy? Probably. Except for the ones that are getting not, but there's going to be more of them that are. Easy peasy. Click. Yes, the customers should be satisfied because they're actually getting more than 32. I don't want to say they're all getting more than 32, but if the average is 32 over, then more are getting averaged or more than less. Okay? Because some customers had recipes that used metric system. 28.35 equals 1 ounce. The refilled boxes were relabeled. The refilled boxes were relabeled. What shape, mean, and standard deviation would go with the amount of grams half? Well, let's go back. The shape is, I'm going to go with approximately symmetric. If you want to say skewed left, and I'd probably say approximately symmetric with a possible outlier. The new shape is going to be symmetric with a possible outlier. Whatever you said the shape was, say it's still going to be the same. Okay with that? So shape. Same as it was. You're not going to say that though. You're going to say whatever you say the shape is. I would say approximately symmetric. Possible outlier. Center was 31.7. We added, sorry. Let me erase that. We added, we added 0.5 to it first, and now we're going to convert it to grams, 28.35. So there's my center. I'll put this in non-hieroglyphics in just a second. The spread or the variability is going to be 0.35, and we're not going to add the 0.5 to it. So here we go. The shape is the same as the original distribution, roughly symmetric, single peaked with one apparent low outlier. I don't know about it being apparent. I don't like that word, but the mean is 28.35 multiplied by the 31.7 plus the 0.5 because we adjusted for the filling, which is 219.87. The standard deviation is now the 28.35 times the 0.35. Don't put the 0.5 with it. There will be a bunch of you knuckleheads that do. The 0.5 has nothing to do with that standard deviation. Okay? Don't add it to it. You're going to try. Don't. Yes, no, maybe. A lot of pencils. Sorry. It's okay. You're just on the World Wide Web. You're on the World Wide Web. That was a student of mine. She just opened a Dr. Pepper. What's that? Okay, yes. Okay, next time we will. There's going to be other students saying, I wonder who that was. Click. We're good. We're good. Last thing. I'm sorry. They did throw this little deal in here. Okay, so picture this. Picture this. I have all those data values, okay? Data values. Y'all with me? And with those data values, right, we can find the mean and we can find the standard deviation. So we would have the mean and we would have the standard deviation with the data values. You guys know how to do that from Friday. What if I found the z-score for every one of those data values? You won't. We'll just do it this one time, okay? So here are those test scores. Y'all with me? The test scores. This was a 12, I think, right? That was a 12. So if I did 12 minus the mean, 34, and divided by the standard deviation, I would get the z-score for this one. And I think this one was 68. And if I did it for all 25 students, or whatever, 25 students, right, I would have 25 z-scores. And if I had 25 z-scores, listen to what I'm going to do. You kind of just play along with me. I'm not doing all this stuff. 25 z-scores, if I found the average of those z-scores, remember some of them are positive and some of them are negative. If I found the average of those z-scores and the standard deviation of those z-scores. So I would calculate the standardized score for every one of those students, right? Using that formula. I'm going to tell you that the average will be 0 and the standard deviation will be 1, and it will always be like that. It will always be like that. So all of those z-scores that I got, if I took the average of those, it would be 0. And if I took the standard deviation of all those, it would be 1. The shape will still be the same. Notice that I have a 0 z-score right here. This is negative 0.5. This is negative 1. This is positive 0.5. And this is positive 1. You have several that have positive z-scores. You have several that have negative z-scores. The sum of the z-scores would be 0. The sum being 0 and divided by boom, click, click, click. The shape is going to stay the same. The center is now going to go to 0. And the variability is going to go to 1. Add them all up. Remember that variability formula is horrible. The standard deviation formula is horrendous. We're just going to plug it on our calculator, and I'm just going to, and that's going to happen every single time. So that's kind of one of those things like you just know it now, right? Kind of like you guys in pre-cal last year when you were given a sine curve, you knew what it looked like. It started here and it went up and it went back down. And cosine started up here and then went down. You didn't have to plug and chug to try to figure it. You just start memorizing. This happens every time. Okay? Click, click, click. We would get the same results no matter what the original distribution looked like. The distribution of z-scores always has the same shape as the original. It has the same mean, or it has a mean of 0 and a standard deviation of 1. That always happens. That always happens. Can you identify outliers by using the 1.5 rule? Can you make and interpret a box plot? Can you calculate and interpret the percentile? Can you calculate and determine a z-score? Can you analyze the effect of transforming data with addition, subtraction, multiplication, division? Notice these words. Those are test questions, right? Interpretations. Go here, exit.